Chapter 7, Section 6, Exponential Functions, Part 1. Okay, exponential function graphs look like these arcs that never actually touch zero, even though it kind of looks like it to the naked eye. The function for an exponential graph is this y equals a times b to the x power, where a can't be 0 and b has to be greater than 0, but can't be 1. Okay, the most important thing to remember is that the exponent has to be your x. Okay, if they give you a table or an equation and they ask you to identify if it is exponential or not, the x values have to have a common difference, which means they have to add or subtract by the same thing, the way this one is adding 1 every time. But the y values have to have a common ratio, which means a multiplying difference. That is the same. If they have that, then yes, this is an exponential function. Okay. But if they give it to you as an equation like they do here, it has to match this y equals a times b to the x power. Remember how I said to make sure that the x is the exponent? Because this one is not, this is not a function, an exponential function. Okay, so if we look at a, we have to see if the x and the y's meet our requirements. The x's do have an adding pattern. They're adding 1 every time. The y's also have an adding pattern. They're adding 2, but that's not what the rule is. We need the y's to have a multiplying pattern, so this one is not an exponential function. Letter B, we need it to match this y equals a times b to the x power, and this one does. The 3 would fill your a, the 6 would be your b, and then your exponent is an x, so this one is a yes. Okay, here's a chance for you to pause your screen, your video, and come back after you've decided what you think about A and B. All right, letter A has 2 adding patterns. Both the A and the X are adding, so that one is a no. And letter B, if I try to match it with y equals a times b to the x power, even though it doesn't look like there's an A would be 1 in this case, so this is a yes. Okay, a couple of word problems. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week, giving us the function f of x is equal to 30 times 2 to the x power. That gives us the population after x weeks. How many beetles will there be after 56 days? Okay, so first of all, we need to change 56 days into weeks by dividing by 7, telling us that this is actually an 8-week session that we're counting. So 8 weeks is going to be our x value. So we're going to plug that in to our function. So we have 30 times 2 to the 8th power. 2 to the 8th power. This is kind of, let's see. 2 to the 8th power is 256, times 30 gives us a total of 7,680 beetles. Gross. An initial amount of 2 square centimeters of mold was found on a piece of bread. The mold triples every day, giving us the function f of x is equal to 2 times 3 to the x power. To represent the amount of mold after x months, how much mold will there be after 1 year? Okay, so 1 year is 12 months since x is represented by months. So we're going to plug in a 12 for x. 2 times 3 to the 12th power. 3 to the 12th power is actually 531,441 times 2 gives us 1,062,882 centimeters. All right, this would be a good one for you to try on their own. Suppose a culture of bacteria doubles each hour, initially starting with 2,200 bacteria. The function 2,200 times 2 to the x gives the number of bacteria after x hours. How much bacteria will there be after 5 hours? So try this one on your own and come check out the answer. 70,400 bacteria. Okay, last part of part 1 is about graphing an exponential function. There's no special tricks to graphing this. We're just going to use our same table where we have our x values, our y values, and our function in the middle. We're going to use -2, -1, 0, 1, and 2 so that we have some negatives, a 0, and some positives. And then whatever we get for that answer is going to help give us our ordered pairs that we need to put on the graph. Okay, we're going to try one that they haven't done yet. I'm going to create my table and put some lines on my graph. Then we have x. We have 0.5 times 3 to the x, and we have y. -2, -1, 0, 1, and 2. Okay, so if I start by plugging in a -2, I have 0.5 times 3 to the -2nd. Remember that a negative exponent does not give us a negative answer. It actually gives us a fraction. So we have 0.5 times 1 over 9, which gives us 1 over 18. When I graph that, my dot is going to go back to up 1 over 18, which is so close to the line that it's pretty much going to look like it's on the line for us. Okay, then I'm going to plug in this -1. So that's really 1/3 times 1/2, which gives me 1/6. Back 1, up 1/6. 0.5 times 3 to the 0 power, which is just 1, so that leaves me with 1/2. Go over 0, up 1/2. 0.5 times 3 to the 1st, which leaves me with 1.5. And then 0.5 times 3 to the 2nd, so 9 times 1/2, which is 4.5. So I go over 2, up 4.5. Then you can see how it gets real close to 0 and then starts to grow really quickly. Okay, on letter B, it's the same thing, except that this one has a negative. So that means everything, all of these y values are going to be negative. So my graph will actually look very similar, except that it's going to be going down this direction instead. All right, last one for the day, real world problem. Suppose an investment of $7,500 doubles in value every 12 years. The function f of x is equal to 7,500 times 2 to the x models the growth of the investment, where x is the number of 12-year periods. Okay, and then we're going to graph the function. So I don't need anything negative since we're talking about money growth here. So on the bottom, I'm going to put a 1, which is really 12 years because they're saying each x value is a number of 12-year periods. So 1 12-year period, 2, which means 24 years, 3, which means 36 years, and 4, which means 48 years. Okay, and on the y-axis, we're going to put this money. I'm going to start with 15,000. All of these will be thousands. And then 30, 45, 60, 75, 90, 105, 120,000. Okay, so if I do the math just using these 4x values, 7,500 times 2 to the 1st is going to give me 15,000. 7,500 times 2 to the 2nd is going to give me 30,000. 7,500 times 2 to the 3rd is going to give me 60,000. And then 7,500 times 2 to the 4th, which actually jumps me all the way up to 120,000. So you can see the exponential curve. All right, that is the end of part 1. So with that, you should be able to complete page 450, the whole page. So 8 through 19, 21, 22, 25, 26, 28, and you should be able to do the lesson quiz.